Well, it's really a pleasure to be here. I'm really happy that I can be here. So, as we all know, our home planet is changing. We have warmer temperatures, stronger heat waves, longer heat waves, droughts, fires, floods, rising seas, and all these changes in the natural system, or in the climate system, have impacts both on natural systems, like displacing species, destroying habitats, as well as on human systems, affecting food, energy, water supply systems. And but what all this means, all this climate change we're seeing means, the effect on humanity is still a bit unclear. And the reason it's unclear is both because we're not sure exactly what humans are going to decide to do, but also there are some factors of the physics of climate that we don't quite understand. And so there's uncertainty associated with that. These physical changes, though, that we do know about the climate system is they're not spread equally everywhere, right? And they have like regional signatures for sure, and that has regional impacts on the climate. And you don't have to look really any farther than the Arctic to see some of the dramatic changes. So this is an animation of the GISS surface temperature record beginning 1880. You're looking at 5-year running means. The blue colors are cooler than average, and the red colors are warmer than average. And this is showing you the anomalies from the 1950 through 1980 as the base period. So what you see in this record as we go forward in time, the globe is warmed by about 1 degree Celsius or so. But we see that not everywhere is warming equally. In particular, here the Arctic is found underneath this red cap. And so this kind of shows us this phenomena that we know called Arctic amplification, the fact that the Arctic is warming faster than anywhere else in response to, well, increased CO2. But it's really more than that. And so, while the Arctic may feel remote to us, and maybe in this room we feel a little bit closer to it than most, but certainly the general public feels like it's very far away. But we're all very connected to the region for a lot of different ways. Our climate system connects us to it through the ocean, atmospheric circulations, the changes in the ice sheets that we're seeing, changing sea levels globally. But also, human systems are really strongly connected to the Arctic. And I don't want to spend a lot of time on this, but I do want to show a couple graphics that kind of illustrate this fact. And one here on the left is a graph from the U.S. Geologic Survey showing you the regions across the Arctic where there are reserves of oil and natural gas across the Arctic. And these are becoming more accessible given the changes in the climate in the region. As well, on the right here, you can see that several of Arctic shipping routes across here, and superimposed is the changes that we expect in sea ice. And so we see that some of these shipping routes across the Arctic are becoming much more usable for various different reasons. And I promised in strategic plans, et cetera, that there are countries and companies that are planning to exploit these new open shipping routes for economic benefit. And so with that, we're all tied to the Arctic. And with this backdrop, our knowledge of the Arctic system, predictions and projections of the future are going to become even more valuable than in the future than they are today. And so I think this is really why we're here. There's really a need to improve our understanding of the physics of polar climate. In this case, I'm focusing on the Arctic, but so that we can improve these predictive capabilities, so that we can better operate in the Arctic and better understand what our impacts are, what our activities, the impacts they're having on the system. And so with this talk, I was kind of tasked with giving this broad overview of Arctic, past, present, and future as I summarized it. And so I'm going to try to do that, but it's kind of there's a lot to cover, but I'm kind of a sucker for context. I really like big picture and trying to start stories at the beginning. And it's really hard with this one, but in that frame, I'll quickly, even though it's not my area, I will talk a little bit about some of the paleoclimate, and I'm sure there are more experts in the room than I on this. But I thought it was really fascinating with looking at these temperature changes of the Arctic over the last 100 million years. This is an example of the Arctic temperature shown here from a paper by O'Regan et al. 2011 showing the temperature proxy over the last 100 million years. And we start by thinking about the Arctic is not always cold. Right, way back when there were temperatures during the Paleocene, Eocene thermal maximum that reached 20 degrees Celsius or so. And then in the time, moving forward in time, the temperature of the Arctic seems to drop, and we start developing some seasonal sea ice around 45 or so million years ago. Keep moving forward, so obviously the Arctic temperatures have varied quite a bit, and if we keep moving forward in time, we get to more recent times where that are very different from the the beginning of this record, which is, the last glacial maximum showed, really extensive perennial sea ice kind of everywhere across the Arctic. And we use these in trying to understand the Arctic system as a whole. I think these paleoclimate perspectives are really useful, especially in understanding our climate models. And a little bit, just taking a slightly deeper look, closer look at the last glacial maximum in particular, here's a map showing the surface air temperature differences from the pre-industrial run, from Tierney et al. 2020. And what you see is that the Central Arctic during this time, about 20,000 years ago, was about 14 degrees Celsius colder than during the pre-industrial. So that's a lot, that's a lot colder, a lot different from today. But the reason I really show this map is that, in the spirit of this conference about the physics of the polar regions, what's really striking is the polar amplification signal that kind of shows up for the last glacial maximum, where there are much colder temperatures at the polar regions than we found more in the tropical regions. And so this feature of a warmer, a more sensitive Arctic really goes back, and you can find it throughout the paleo record. Now, I really wanted to show this also because our understanding of our hypothesis about why the Arctic is so much more sensitive than anywhere else really are rooted in questions that were being asked of the paleoclimate record. And it goes back to 1896 with savant Arrhenius, who was trying to figure out why, these glacial interglacial periods of the Quaternary, like, why was the Arctic so much more sensitive than that? And in his study, going back 1896, what he really found is that it was the surface albedo feedback, or the progression, the north-south progression of the snow ice line, that was really helping to amplify some of these temperature changes. So our understanding about the Arctic system and why it changes so much more rapidly is really tied to the albedo, the reflectivity, the snow and ice of the region. So that's kind of the starting point. And I don't want to spend too much time here, but I'll try to walk through this a little bit. I tried to summarize that we've learned a lot in the last 100 years about how the Arctic system operates. And I pulled out a couple really what I thought were key aspects of these changes. Let's jump into the 60s here, where there were a lot of studies by Budyko, Rakapova, and others that were really focused on using energy balance models and applying them in the Arctic and to understand the surface albedo feedback. They primarily treated the surface albedo feedback as a function of the temperature of the region, but those studies really helped to show that surface albedo feedback was a really key part of the climate change there. So we have that. Now, a lot of the next 10 or so years, a lot of the advances that we made were kind of building on top of these energy balance models. So one example of that is Weatherald of Manabe in 1967, and this focused on including vertical heat transport, or convection, the connection between the surface and the atmosphere within these energy balance models. And I know if some folks are familiar with that paper, that's the radiative convective equilibrium paper by Weatherald and Manabe. And so it's usually thought more of a tropical concept. But if you dig in the back of that paper, some of the work that they did in there was to show that because of the strong static stability in the polar regions, that when they perturbed the surface albedo, there was a bottom heavy or surface kind of trapped warming response to that. And so they showed that in 1967, and was because, and explained it as part of the strong static stability of the polar regions. So continuing with advancing these energy balance models, Sellers 1969 added in horizontal heat transport. They used a zonal mean energy balance model, and what they added, they represented polar heat transport as a diffusion equation that was proportional to the equator to pole temperature gradient in there. And one of the things that they really showed there is that the way that the polar heat transport is represented in the model has a really strong effect on the Arctic temperature. It's very sensitive to that, the way that that's treated. And kind of the realization, and this is where, in 1975, Weatherald and Manabe, they published the first study of Arctic amplification using a GCM. And what was really interesting is that their decision to apply a GCM to this was based on some of the results from Sellers 1969, where, because of what we found that the importance of polar heat transport, they really thought, well, hey, we should do better at representing the atmospheric circulation than just using a diffusion equation. We need to represent the episodic variability in the system. And that motivated them to apply a GCM to this problem. What they kind of learned from that first study is there was no ocean heat capacity in that first simulation. But what they reproduced is that bottom-heavy surface warming profile that we see in Arctic amplification. So they knew that not having a ocean heat capacity was a problem. So in 1980, Manabe and Stauffer, published some simulations where they use ocean heat transport, and not ocean transport, ocean heat storage. And when they had heat capacity in the ocean, they were able to represent the seasonal cycle much better. They have a seasonal cycle in the model, and it really showed that there was this focused warming in Arctic amplification in fall and winter time, and more muted warming in summertime. So to this point, we haven't thought about, most of the studies haven't really thought much about ocean heat transport. And so there was a series of studies in the 80s led by Washington and Meal that focused on exploring the role of ocean heat transport. And how they set up the series of papers was looking at different complexities of ocean models, from a swamp ocean to a mixed layer ocean, then to a fully coupled ocean that had dynamic heat transport. And what they found in that is that when you start including ocean heat transport, it really changes the base state of the model, the Arctic that they get. They got a warmer Arctic than they did without it, and they also got a reduced sea ice cover. And so that ended up changing what the sensitivity of the Arctic that they were getting. They were getting, in their simulations, their Arctic was less sensitive to doubling CO2 when they included these the ocean heat transport. So here at the end here, in the late 80s, this is where multi-model intercomparisons really started to emerge and are traced back to, and I think they continue, they continue through the 90s, it kind of dominated the 1990s, and continues to today. And I know there's some fatigue around model intercomparisons, but I do think they definitely have value, especially in trying to figure out, the uncertainties of some of these kind of projections and why are models different. But that's where that kind of starts at. Moving to the 2000s, I think there were a lot of paradigm shifts in that time that were really important, and some that we're still thinking about today, and I'm sure in this conference and the rest of the week we'll talk about and think about more. And one of those is that there were some model simulations, idealized as they were, that show that you could get Arctic amplification happening in a model without the surface albedo feedback. Previous studies had kind of thought that that wasn't possible, but Alexeyev, 2003, and some others showed that you could get that, and that was related to the moist static energy transport that we had that in the model. So that was one thing that shook how we were thinking about this. And the other is that we now had multi-decadal observations from satellites that showed all these changes happening since the early 80s. And now we were starting to use those to do studies that were able to detect, for instance, in 2009, the emergence of surface-based Arctic amplification that we found in Ceres 2009. And so we continue to study Arctic amplification today, and I think that, if I were to put a title on what we're doing today, it's kind of like using models and observations synergistically and trying to move towards more interdisciplinary studies. And so I think that's where we need to move and continue to. So kind of, let's see here. So, that's a lot of information. It's a lot of, what have we learned from all that? Can we put it all together into a conceptual, consistent picture of Arctic amplification? I think we can. I think we have. And so I did this, led a review paper on this in 2002, a few years ago, where we tried to take what we knew and put it all together. And I'll be honest, that a lot of these concepts that you see here on this graph, which I'll walk through, are all rooted in that Manabe and Stauffer paper in 1980. So there's really strong ties back to what they were able to, the explanations that they provided in that early study. And so try to put this conceptual model, there are five key concepts here, and I'd like to put it into a story, but I don't think I have time, so I'm just going to read them out and then we'll keep moving. But first we have concept one, which is we have positive local feedbacks in the Arctic that help amplify the initial response to increased CO2. And that includes clouds and water vapor, but also sea ice is really the most important of that, the largest contribution to that. Then secondly, all those feedbacks and the initial warming of CO2, initial response to CO2 is a warming in the Arctic, but then the strong static stability of the Arctic kind of restricting the vertical mixing, and that helps provide a bottom surface-based warming profile, warming change near the surface. So the third concept is the importance of seasonal energy transfer. So when you melt back the sea ice, you have much more sea ice loss that happens in summertime. So less sea ice loss in summer, there's a lot of energy that gets put into the Arctic Ocean. Because of the heat capacity of the ocean and the melting of sea ice, there's not a lot of warming there. So that energy kind of stays around. It lengthens the melt season. It makes the sea ice freeze a little bit later. And that is a very important process that kind of transfers some of that energy that was absorbed in summer into fall. And that has a lot of implications to how Arctic amplification evolves. Now, moving from kind of the local perspective, there are ties of, concept 4 is about the ties of this Arctic amplification to transports from lower latitudes. In particular, if you think about, you increase CO2, you kind of change the character of the air globally, warm and moisten the air everywhere. And so that means that as you have polar heat transport, you're actually changing the character of the air that's being brought into the Arctic. And importantly, it's much moister than it used to be. And that changes in polar, specifically latent heat transport then itself, drives additional warming through what we've called the water vapor triple effect, the changes in water vapor and clouds that happen. Then lastly, that change in polar heat transport and that warming activates local feedbacks. So there are really important interactions between how the lower latitude transfer of moisture into the polar regions kind of interacts with the system, the Arctic system. And so that is kind of one way we can put together everything we have. And so this concept puts out some predictions or ideas about what we should be seeing in our observations. And so the question then, next question I'll ask is, what changes have we been observing? And have we observed what the studies are showing? And I'll say, spoiler alert, the answer is yes, generally. But so first, we want to look at the vertical structure of the warming, and this is a plot from the ERA 5 temperature record. And you can see that the Arctic's here on the right, and it's from these red colors here show you the warming signal are about 0.8 Kelvin per decade here, and it has the strongest warming at the surface, and it decreases as we go vertically, upwards in altitude. And so we see this is kind of the vertical structure that was predicted by those early studies. Secondly, the conceptual picture also kind of predicts the seasonality of the warming. And you see here, this is the GISS temp record showing the different seasonal warming patterns over the last 60 years or so. And you see that the strongest warming here are in wintertime and fall time that we see, as is suggested by our understanding. You could also see it in the zonal temperature anomalies here, where polar to 70 shows much greater warming over the last 60 years. We've also observed a lot of changes in sea ice. And so here's an animation, and I really like staring at this one actually. This is showing the age of sea ice from 84 through present, or roughly. And the whitest, brightest ice here is showing you the oldest ice, that's 4 years and older, and the grayer colors are showing you youngest ice, the seasonal ice. And what this animation shows as we get closer to the beginning is that from 1984, the perennial ice cover, this oldest ice cover that was 4 years and older, was about 20% of the total ice cover. But the changes that we've seen, it's now about 3% of that March ice cover, the oldest sea ice, the 4+ and older sea ice. So we see these really large changes in sea ice age. You could also glean some of the changes and reductions in thickness or the thickness and concentration that we've seen. But one thing, I got lost a little bit for a few minutes while I was putting the talk together on this slide in particular, because I really like that this is showing you weekly time steps of the sea ice, the sea ice age. And what becomes really important to see, especially as we get later on, are these kind of episodic export events of this older ice from the central Arctic into the Beaufort Sea. And I think that that's something that, especially as we move forward in time, it's going to be something we need to think about a little bit more. It's going to be really important part to make sure to see if our climate models are actually representing these processes and those episodic transport events. All right, I'm going to keep moving. So not to be left out, we have seen declining land ice as well. It's really hard to cover everything, but we see, this is animation from showing the NASA GRACE data since 2002, and we see that on average there's about 269 gigatons per year of mass loss that we've seen from Greenland ice sheet. It's primarily on the edges with a little bit of blues you'll see in the center of the continent. But also there's been some really big years, like about more than 500 gigatons of mass loss from the ice sheet in 2019, and that contributed to about a 1.5 millimeters of global sea level rise just from that one melt. And to put that into perspective, since we're in California, that's about 4 feet of 1.5 millimeters global sea level rise is about 4 feet depth of ocean water over the state of California, water over the state of California. So it's pretty deep, actually. So with those changes, and I know I left some out, where are we going to? That's kind of where we are, but where are we heading to? And so kind of the most obvious and evident ones that I've already alluded to are the changes in temperature and the changes in sea ice concentration, average changes that we've expected. And these animations are from Zachary Labe from Climate Viz. And I did, by the way, if anybody's been to his site, I bought him a coffee in using these. Thank you. But these show the general character of the changes you expect to see in the Arctic. For temperature, you're looking at October, November, and you can see some of these large changes as we get later in the century. And you can't see it as well on here, but from some work, I think something really important point to point out is that the places that tend to warm more are actually the places where you take sea ice and turn it into sea water, right? Places where you used to have ice, but now you don't. Those seem to warm a little bit more. And I think that, and we'll hear about from Michael in the next talk, and I think that's actually a really important part of what he'll talk about, I think. But then also within the sea ice concentration graphic, you see generally the decline is from the Pacific sector towards the central Arctic, leaving the last kind of bastion of sea ice, if you will, off the north coast of Greenland here. So those are some general changes, kind of the direction that we're going, but, oops, I skipped a slide. But also there are lots of other changes of importance that there aren't time to go into that I hope other talks will be able to cover them. But we see that the changes in the Greenland ice sheet that we saw over the last 20 years are going to continue to decline, especially reductions in elevation, around the edges in particularly strong. We have declines in the permafrost cover, right? Very large reductions in the volume of permafrost that are going to be important, and also changes in just the general character of the sea ice. Right, potential for expecting the first sea ice-free day within the next decade. So we have all these changes, and I think, well, the best takeaway message, since you can't cover all these in the detail one would like to, is that the whole system is changing, and where all these changes are interconnected. And so really exploring those interconnections, I think, is what we need to do in order to advance or to reduce the uncertainty in the projections that we have in the future of the Arctic. So speaking of uncertainty, we know there's a lot of uncertainty, a lot of those projections of the future that I mentioned. And so, generally speaking, from the crowds that I run in anyway, when we have there's an uncertainty or an intermodal spread and like the temperature change of a region of the Arctic, we try to go to radiative feedback analysis essentially as a way to understand that. What are the different processes that are contributing to the top atmosphere energy budget that are resulting in the warming? And so here's a paper from Lily Hahn, who's in the room, and she looked at this for CMIP 5 and CMIP 6, but this plot is just for CMIP 6, and this is showing one of those radiative perturbation feedback analyses where you separate out the different contributions, and kind of the takeaway message is that the largest, even though we feel like we know a lot about the albedo of the polar regions, I mean, it's obviously still the largest contributor to the intermodal spread. And that's shown by this, the box and whisker plot, and also some of these contributions of, the warming of a model due to the surface albedo feedback here is about 9 Kelvin, but the total warming is about 18 Kelvin. And so we're seeing that, up to half of the warming in some of these models is because it's attributed directly to that surface albedo feedback. But I think in the time that I have left, what I wanted to be able to do is to lean forward a little bit, and because I think while these radiative feedbacks, they're really important, right? But it doesn't quite get us there. Where we want to go is to causality. We want to know what is actually, what is the fundamental physical processes that are causing this? Because knowing that this is a difference, that we have anywhere from about 3 to 9 Kelvin differences in the warming that can be attributed to the surface albedo feedback, that doesn't tell us what's melting the sea ice, right? And this isn't all sea ice, actually, but this doesn't tell us important questions like what processes are most important for melting the sea ice. And I think that getting to that level is what we need, where we need to go, what we need to focus on. So with that, and I don't know, how am I doing on time? 5 minutes. 5? All right, that'll be good. Well, I'll stop at 5 minutes. So in the remaining time, I wanted to show a couple snippets of ways that we're thinking about this problem within the folks that I collaborate with. In trying to go past just looking at surface albedo feedback as the radiative perturbation that's driving Arctic change and trying to understand what's driving the melt of sea ice. So the first one, this is I want to highlight some work by Dorian Kim, a postdoctoral researcher at NASA Langley Research Center, and she started working. We started this work by wanting to know what are the differences in albedo in the Arctic, and what causes those differences across models and with observations. And so what she developed using this picture up here, where we're trying to characterize the albedo of the Arctic region by breaking apart the Arctic Ocean albedo into the ocean area and the ice area, and then developing several terms. And so we end up having 5 terms here because of, to get the equation to close. But in the end, there's only 3 that are really important. One is the ice albedo itself, right? The second term is then the concentration of the ice within this ice region area. And the third then is the area of the ice region itself, right? Essentially ice extent. And so if we start all these, each of these different dots represents a different model, CMIP6 model, of course. And then if you look at the right side of these, the squares represent the CMIP simulations. And so if you compare, this is showing the intermodal spread in those, and if you look at there's substantial spread in both the ice albedo term. The ice concentration term is actually the lowest, smallest contribution in the intermodal spread, and then the largest contribution in the differences in albedo across these models is the extent of the sea ice. Maybe it's not surprising, but it's something that we show that the different areas of the sea ice, the different sizes of the sea ice region area are generating a lot of uncertainty in the albedo in these different models. But also, what's really interesting to point out here is the circles are showing you the AMIP simulations, which are atmospheric model only, and these are forced. Those models are given all the same sea ice concentration and extent, and you can see that those circles for the concentration and for the region area all will collapse to 0, to not being different, which is good. You see these very large differences, intermodal spread in the ice albedo itself. And so they're actually the same width as in the coupled experiments. And so, the takeaway from this is that, we really need to focus on, these parameterizations that are important to distinguishing sea ice albedo. It's making a very strong contribution to the uncertainty of the size of the albedo of the sea ice. And so another way we've applied this decomposition approach to changes in albedo as well, and here we're just showing the 3 important terms, albedo, concentration, and sea ice extent. On the y-axis is this delta shortwave alpha. It's the radiated perturbation at the end of century due to the change in the surface albedo. So you can think of it as the magnitude of the surface albedo feedback, essentially. And on the x-axis here are the total albedo trend, the ice albedo trend, the ice concentration albedo trend, and then the albedo due to ice extent. So the first kind of thing, and the blue line is series observations, so satellite data of changes in albedo, and ERA 5 is the reanalysis data, meteorological reanalysis. And so the first that you see is that, if you take these trends from the satellite data record over the, we focused the years 2000 through 2023 because of the satellite data record. But if you take the trends in these model simulations from SSP 8.5, you see that models that have a stronger trend in between 2000 to 2023 have a stronger surface albedo feedback by the end of the century. So this suggests that what's happening right now is telling us something about what we can expect in the future. And if you compare the top left to bottom right, most of this is because of the ice extent changes that we're seeing there. So the ice extent term albedo contributions are the most important. But one thing before I move on, I want to point out is the ice albedo itself. So most of the models have a very small trend in the albedo of the sea ice changes over the last 23 years or so, but series is here up in the upper end of the models. And so there's some missing contributions of the ice albedo changes that we think that are in the models. And also, just as a word to anybody using ERA 5 to look at the Arctic, is they have the opposite trend of ice albedo trends, where their ice albedo is actually increasing. And there are reasons for that we can talk about offline. So I think I'm going to skip this one because, I have 3 minutes. So one other question that, I'll stop here after this one. But one other question that we're asking is, why does the sea ice parcels actually melt? And why do some parcels survive the summer melt season, and why do some make it throughout the summer melt season? And we've adopted this concept called survivability, where we're taking sea ice parcels, which are represented here on the upper right-hand corner, essentially from National Snow and Ice Data Snow and Ice Data Center has a data product on that, and we've co-located many different satellite and reanalysis data products to provide us kind of an idea of the temperatures and the winds and the surface energy budget that are these parcels are experiencing. And so we can take these parcels and we can take the total number of parcels in any year, in any region, and we can divide it by the divide the number that survive by the total, and we get a percentage or a likelihood that these parcels survive. So we try to use this concept to track individual parcels as they drift around the Arctic and understand why some of them melt and why some survive. What we're finding, one example of this work is that we've been able to separate out into the parcels into different classes. Like in these probability distributions, we're seeing that multi-year survived, first year survived, multi-year melted, and first year melted. And the left panel showing sea ice growth in winter. So what's really interesting are two things here. Is that one is that it does seem that parcels, makes sense, parcels that grow more in winter have a higher tend to have a higher likelihood of surviving the summer melt. But I think the cleanest signal, because you see there is some overlap between these PDFs, is actually parcels that don't survive, parcels that melt out. Not all, they tend to, some of them have don't grow during winter, in fact. And on the right, we see that there's very strong differences in the albedo of these parcels in early summer. And so this is suggesting that the surface albedo feedback of these parcels actually is a really strong factor in driving whether parcels survive or parcels not. And so, so one thing that I'd really like to do in the future is to be able to look at some of this within the model context and understand how models are doing when they are vectoring these parcels around. So let me skip that one and just close. And this one is for the oceanographers in the room. The Arctic is changing fast. And I think we need to focus on bringing together the processes that are causing the melt with the magnitude of that radiative feedback that I was talking about. And I think there are a lot of opportunities really for cross-disciplinary interaction. And I'm really excited to be able to participate in the rest of this conference as well as the rest of the program. So thanks.
Very nice way to get started. If that works.
We can hear you, I think.
We can hear. We have plenty of time for questions. That's actually quite the point. So feel free to ask anything. And if there are people on Zoom, I was told that you should be able to raise your hand and unmute yourself to ask questions. If there's a chat, I'll try to keep an eye on that. Yes, Paul.
I want to encourage people to...
Yeah, and if you ask questions, there are two microphones on both sides of the room.
And that way the people on Zoom can participate. So thanks Patrick, and thanks Hélène for all this organization. I just wanted to bring up a theme that's come up a couple times in the program, and that is whether we really need an Arctic inversion to have a strong lapse rate sea ice albedo feedback. So Ian Eisman and Jen Kay presented evidence that, basically model-based evidence, that you didn't necessarily need a very stable Arctic to have a strong lapse rate feedback. So I don't know if that's and that state dependence is really a key theme that's come out of a previous few weeks. So just thought I'd throw that comment out there to start and see if you have any comments.
Yeah, that's really interesting. I'd love to think on that more. But one thing that we did some work on the surface albedo feedback. Oh, sorry. Let me go back. Lapse rate feedback in particular. A few years ago, one thing that we found when looking at the spatial structure of those changes in the lapse rate feedback is they're not distributed equally. The lapse rate feedback tends to be strongest in the marginal ice zone regions, right? And that's because it's really strongest in the marginal ice zone regions where you're losing the sea ice, because that's the place where you're seeing the strongest changes in surface temperature, right? From ice cover, which is cold, and then to the ocean temperature. And so I think that, that work was model-based, but I would say we saw that what was more important in driving the magnitude of the lapse rate feedback was the changes in surface temperature versus the changes in the atmospheric temperature. So I guess with that, talking about whether you need a really strong, stable stratification to get a strong lapse rate feedback, I would guess probably not, if the surface temperature changes are what's driving it. But also, in that sense, the surface albedo, the contributions of the surface temperature change to that lapse rate feedback is going to be kind of capped, because you can only get so warm. Right? The Arctic Ocean in short time is only going to get so warm, right? It's going to be kind of close to freezing or maybe a couple degrees Celsius above. And so that actually speaks to like models with the stronger lapse rate feedback might actually probably have a colder sea ice cover to start with to get that larger difference in temperature change. Those are some, so I think I might be on the camp where I don't think you need to have a strong static stability to get a strong lapse rate feedback. But also I would add that, and I'm not ready to present an argument here, but you know, I think there's an important thing about the lapse rate feedback. So I know there's a bunch of people in the room that maybe not be as familiar with the lapse rate feedback. So like the lapse rate feedback is the radiative perturbation at top of atmosphere that happens because there's a non-uniform change in temperature. So there's a vertical structure of the temperature change. And the lapse rate feedback is the radiative perturbation that happens because of that vertical structure of the change. And so I think what's really important to think about is, well, what processes are actually driving that vertical structure of the surface temperature change, right? Is it the heat transport from lower latitudes that's changing warming the atmosphere? But it's really, again, the lapse rate feedback, if it's driven, the changes are driven strongly by the surface temperature changes that the model's producing. It's really those surface processes that are really important to the lapse rate feedback. So I think on this theme that I was presenting on surface albedo feedback, I think really understanding more, and I know folks in the room have worked on that a bit, for sure, but understanding those processes that are really contributing to that lapse rate feedback is really key. Yeah.
Thank you. Other questions? Yeah, if you want to use one of the two mics so people online can hear you. Thanks.
Thanks for setting the stage so beautifully. I kind of want to follow up on Paul's question about the vertical structure of the temperature change.
Yeah.
You showed the ERA 5 trends in the sort of zonal mean atmospheric temperature. And do you think that's like adequate for looking at what's going on in the Arctic region? Like, is that more of a model quantity versus are there enough observations sort of going into that assimilation system that we should just take that at face value? Some people are kind of skeptical of reanalysis-based trends. I don't have a strong opinion, but...
Oh, okay. Well, I would say that you definitely need to be skeptical of reanalysis, just to start. I think that those trends in temperature, you know, you have to know that some things in the reanalysis system are things that's maybe a bit more trustworthy and some things aren't. Obviously, I showed the example with the surface albedo, and surface energy budget in the Arctic isn't something that I would trust, you know, blindly from marine analysis. I mean, temperatures would probably be better, but anytime you think of trends, like I know I showed the trend, that's really easy. Like, you know, I'll take a step back, right? We don't have a lot of data in the Central Arctic, specifically of the vertical temperature structure and the changes over, you know, decades. And so that kind of necessitates the need to kind of pull in reanalysis so that we can look at some of these things. But you know, I would say like from the way I was using it, it's okay. But I think we do need to here anyway. But I mean, temperature is one of those fields that probably be better. But I know that there are lots of biases and errors in like the lower boundary layer temperatures in the Arctic. That if you're focused on that the structure of the boundary layer near surface, that would have, you know, you have to be very careful about using that, and you want to make sure that you're using, you know, whatever actual observations you have from radiosondes, etc. But those trends do align with what we see from AIRS. And again, satellite AIRS retrievals of temperature also have their own kind of idiosyncrasies, especially associated in the boundary layer, right? Because they only have the resolution's not that fine to be able to capture a lot of the fine scale structure that we see in the boundary layer. So, I mean, in the end, I'd love to see us to improve the reanalysis, and in particular, you know, if we could get, I don't know how to get more radiosondes in the Central Arctic, but if we could, that would be like the way to do it. And whether, I've thought about this, but I don't have a bucket of money to like make it happen, but if there's a way we could get some autonomous systems to launch radiosondes for us, then we could just leave on the ice like we do sea ice movies. I don't know. But I think that would be, you know, so I guess I trust reanalysis, but only so far. Like, to summarize.
Thank you. Other questions? Yes. There's another mic here on that side if it's easier. You can take mine. Yeah, take mine. Why do you look here?
Hello, so I'm François Massonnet. We've been in touch, and I would like to congratulate Patrick because he's been one of the few to actually request an opportunity for the CMIP7 CI SMIP. And so the opportunity will be called causality of polar amplification, and one of the characteristics of that opportunity is that there will be many daily sea ice fields that have been requested, but also many daily fluxes. And so I was a bit curious about what kind of methods you envision to use to extract causality mechanisms from this daily data. Are you thinking of things like Granger causalities or Liang-Kleeman methods that are specifically designed to disentangle what is cause and what is consequence, or do you have something else in mind?
Thank you for that. Yeah, and so I had intended to say something about that in the talk, but so, yeah, and I have an assignment, Patricia, we have to look at the paper. But so coming out of, with the next CMIP7 data call, the polar, as you mentioned, the polar amplification causality opportunity, what the focus of it was to have model output that is on daily timescale from both the atmosphere, ocean, and sea ice. Because a lot of the CMIP outputs that we've had are generally monthly mean scale. And so when you try to understand, like a lot of the examples that I gave here show that, the episodic variability is really episodic events, and that variability is actually an important contributor to changes in sea ice. So let me show you one example, I guess. So thank you for this. I get to show a slide I skipped, which is about this. So one of the things I mentioned in the conceptual picture is that these remote local interactions are really important, and that is like what happened, the movement of air and moisture and energy from lower latitudes into the Arctic region is an important contribution of Arctic amplification, but we happen to know that those happen in episodic bursts, right? They don't happen, monthly mean advection doesn't tell you a lot about what happened, to bring that transport there. So one example of that is atmospheric rivers. And this is some work that was recently published, a study led by Pengfei Zhang in GRL. And what he did mostly was drive the sea ice model with atmospheric reanalysis over the last, over decades, and then go into the data and find these atmospheric river events, and then composite the sea ice tendency terms from the sea ice simulations around these events, and to be able to figure out, well, what is the atmospheric river actually doing to the sea ice? And so in this plot in particular, you see there are tendencies for sea ice concentration here and sea ice thickness that happen in response to an atmospheric river event. And so sea ice tendency, what you can see is that there's, let's just focus on thickness here, is that there's this, during atmospheric river events, there's a strong increase in sea ice thickness in the Central Arctic in particular as the ice is kind of pushed there, and that's primarily a dynamic mechanism, right? Then in the marginal ice zone, there's a lot of thinning that happens during these events because of changes in, the growth and the melting of the sea ice that happens due to thermodynamic mechanisms. So these type, having that daily output will allow us to get at what these episodic events, how they're actually melting the ice, and how that then influences, right, the surface albedo feedback that you see. It's all about getting to the question about what's melting the ice. So this is one example of how we can resolve these episodic events that are happening. And then, because I don't think we have a really good idea of are these episodic events in the models? I mean, I know Brian Cardinale and Brian Rose have some really nice studies on this using one model that show the polar heat transport and that the vertical structure of it's really important. But I don't think we know like how different these models produce the episodic events, like how different they are and what their impact is on the sea ice and how that varies across the models. So that's one idea that I was planning to use it for. Thanks for the question.
Yeah, thanks a lot. I think we should continue. Thanks a lot, Patrick, for setting up the stage beautifully. Let's thank him again.